So I'd like to thank the organizers for inviting me here. So what my talk will be focusing on is on the green hydrogen economy, how green and how economic. Now we all have been hearing since the last session, hydrogen is green, hydrogen is economic. So we are going to put a question mark on that, specifically with respect to the Indian context. So here comes our research. So I'm basically leading the energy systems modeling lab at IIT Roorkee. We were doing this kind of analysis and trying to see we should not be just swayed away with the global trend. Let's do analysis for India. Let's see what the numbers are for India and then make an informed choice. So most of the data that you would be seeing in popular literature has been either from the IEA reports and other things, which are not particularly for India. And what we'll try to show you are some of the India-specific numbers, specifically with respect to green hydrogen. And let's stop at green hydrogen, green ammonia, because since the last session, the spotlight has been on ammonia. So let's focus on ammonia. What if we are making ammonia from biomass? What if I'm making ammonia from electrolyzers? Now electrolyzers is just a way in between. We are basically using some kind of electricity. Now this electricity can come from the grid, which is going to come from most of the cases. What if it's going to come from solar, solar plus grid, or solar plus batteries? Let's have a deep dive into it. How does the economics and the emissions change when we do this kind of transition? And finally, when I talk about energy storage, the first thing that is going to come in all of your mind is batteries. Is that the only medium for storage? Probably we need to broaden our thinking. We should think about solar thermal, pumped hydro, and this is what I'm going to talk about. So here we are. So basically, let's start with biomass to green hydrogen and ammonia. I believe we have heard a lot about ammonia. I don't need to focus on that. It's one of the major chemicals. So we wanted to do an analysis if we were producing ammonia from biomass. And we did it with the Australian mining giant with the name Roorkee, which is one of the leading ammonia manufacturers in the world as well. So we wanted to see if I'm using biomass for production of ammonia. The route is simple. You're having biomass, go through biomass gasification. Biomass gasification gives you synthesis gas. Condition that gas to produce hydrogen. Hydrogen take it to Haber-Bosch reactor and produce ammonia. But the key here was we wanted to compare the route among different nations. What if I am comparing this route in Australia, where we have a lot of eucalyptus, to India, where we have a lot of straw? It's much of a problem in here, especially in the northern part of the country. Compare that with Brazil, where we have a lot of bagasse. Three different biomasses, three different supply chains. So we wanted to compare the same production of ammonia from three different biomasses across three different locations, and we wanted to see how the supply chain affects, how does the costing affects, how does the emission affect. So we did in-depth simulation. This is what we are good at, simulating complex systems. So this is what the systems look like: biomass cultivation, a specific kind of gasification, gas conditioning, leading all the way till Haber-Bosch reactor producing ammonia. I'm not going into details of this process. Let's come directly to the results. So here's a result that would be of importance. What you have on the graph on the right is basically a trade-off between economics and emissions for the three different routes in three different countries: India, Australia, and Brazil. What you have on the x-axis is the global warming potential, which is the kgs of CO2 per kg of ammonia. What you have on the y-axis is the dollars per kg of ammonia. A traditional price can be taken as $500 per ton. That's what the market price currently stays at. And if I talk about the emissions, the current ammonia emissions are roughly around 1.8 to 2. That is what the baseline is. So what do we see in here? If I produce hydrogen from biomass in India, it's going to be really economical, almost very close to what you get. Still economically dearer, but still better than other places, because manufacturing is easier, supply chains are cheap, labor is cheap, technology is cheap. But what about the emissions? It's almost very close to what I am getting from natural gas-based hydrogen or ammonia. There are reasons for that. You can go for a country like Brazil. It's very clean, but economics is not very much in the favor. Go to a country like Australia. Biomass is not the best way to do it, either economically or emission-wise. So if we are going to say that emissions are going to be, say, for electrolysis for such and such country is going to be same for India, possibly no. We have to do our own analysis, because India, things are very different, and when it comes to emissions, it's a whole lot different. So here are we have published this in a lot of peer-reviewed journals, or some of the top journals in the world, so these results are accessible. case study 2. Now let's come to electrolytic hydrogen or ammonia. You have electrolyzers which are taking some kind of electrolysis or some kind of electricity. Now this electricity can come from the grid 24 hours, from solar 7 hours a day, from solar plus grid 7 hours of solar, 17 hours of grid, or solar plus batteries. Now this electrolysis is going to produce hydrogen, combine that with nitrogen, take it from the air using an air separation unit, simple Haber-Bosch reactor, produce ammonia. This is what we are looking at. We did an India-specific research on this, where you can see the data came from the leading companies in India, so the numbers are from the market directly. We are not assuming $250 per kilowatt for the price of electrolyzer, but we are assuming $2,400 per kilowatt, which is the market price for this analysis. Again, when we do a typical life cycle assessment and costing, we take all the things into an account. The catalyst, the deionization, the auxiliaries, the balance of plant, we modeled everything ourselves. All the equipments are sized by ourselves. So we know what the size is, what is the material going into it, and how much will it cost. So here are some of the results. So first, have a look at the x-axis, which is the different cases. On the y-axis towards the left, you have the levelized cost of ammonia, which is called LCOA, dollars per kg of ammonia. What you have on the right is the CO2 footprint in the kgs of CO2 equivalent per kg of ammonia. This is what I want to compare. So first, have a look at the conventional cases. Hydrogen in India can be produced from natural gas. It can be produced through coal gasification or some kind of naphtha reforming or fuel oil. The price I have taken to be $500 per ton, and the emissions vary from 1.6 to 3.8. So this is what the conventional case is. Now if I go for grid-based electricity for hydrogen leading to ammonia production, the price is going to almost double. What happens to the emissions? Almost 4 times. So if you're thinking I'm using electricity from the grid and it's going to give you green hydrogen, wake up. Our grid is very much dependent on coal. Lot of inefficiencies, doesn't make a case. Go for a solar case. I'm running my electrolyzers from solar, ramp down the capacity to 10% during the night time, so you have a little bit of storage that is needed, and then produce ammonia out of it. The price becomes 4x the market price. What happens to emissions? Are they zero? No. There's nothing as net zero. There are going to be significant embodied emissions. Construction of solar panels takes in energy. Mining of silicon takes in energy. This is what we have accounted for. And there it's going to be 0.4. So we have almost 75% reduction from the base case. Take the third option. 7 hours of solar, 17 hours of grid during the night time. Again, the price is 2x, but the emissions are reduced because in the daytime I'm using solar. The last case, solars plus batteries. 7 hours of solar, the remaining 17 hours of battery. It's a hypothetical case, but we wanted to see, like if you have a huge solar plant which can store enough for the nighttime batteries as well. Again, the cost is roughly equal to 7 hours of solar. That gives you, why would you go for solar plus batteries when the LCOE is the same? Just go with solar. What happens to emissions? 0.9, because batteries construction is also very energy intensive. Batteries tend to degrade quite fast. They need to be replaced as well. So this is some kind of eye-opening things that we got, and it all has again been published in a lot of literature which you can access. Then the third thing. Now if I'm talking about electrolytic hydrogen, it needs a steady supply of electricity, which entails I would need some kind of storage. And as I have told, when I talk about storage, I talk to people, the only thing that they are capable of thinking is batteries. We wanted to broaden the horizon. Let's look at other options as well. Of course, there is lithium-ion batteries. There could be molten salt storage. There could be pumped hydro. There could be redox flow batteries. And there could be compressed air storage as well. All these kind of storage have big storage capacities globally. You don't hear much about those except for pumped hydro in India. So let me give you an idea. So when I talk about pumped hydro, it's basically having 2 reservoirs at a head difference. So whenever you have excess electricity, pump water to a high reservoir. When you need electricity, just use it as a simple hydropower plant, run turbines, produce electricity. Batteries, we all know about. When I talk about molten salt, it's basically heating some kind of phase change material with the direct sunlight to almost 500 degrees Celsius during the daytime. In the night time, let it cool, produce steam, run turbines, produce electricity. Something similar for compressed air storage as well. Whenever you excess electricity, use it to compress air in some kind of underground reservoir. Now let's talk about the results. So again, similar kind of results. You have the 5 storage options in here: pumped hydro, lithium ion, vanadium redox flow battery, compressed air, molten salt. What you have on the x-axis? Global warming potential in terms of kgs of CO2 equivalent per megawatt hour. That's basically the carbon footprint. What you have on the y-axis is the levelized cost of storage, LCOS, which is the average storage cost that you're going to get over the lifespan. The capacity that we considered in this case was 250 megawatt of storage that was done. And if you see which option comes out to be the best for India, pumped hydro. It has the least emissions and the least cost, much cheaper than batteries. This whole results were, or this whole analysis was done in collaboration with the industry, so the numbers were coming directly from the industry, and that is why you would see the numbers are quite high as compared to what you would see in the popular literature. But believe it or not, batteries are way too expensive even today. No matter what the popular literature says, how good China is manufacturing, they're way expensive. Maybe think about pumped hydro, which could be an indigenous option. Technology is available in-house. You just need 2 heads difference, and you don't need to have a flowing river nearby. So that could be one option to bring down the cost down. And again, this again has been published recently, and the report was released by MNRE Secretary himself a couple of months back. So this again is available in the open domain. So to end the presentation, so there are 3 points. First thing is the emissions are going to change with countries. If something is going to be environmentally friendly in the US, might not happen in India as well. When it comes to electrolysis, be careful what the source of electricity is, because that is going to make a lot of difference. Third, even if you want to go for electrolysis, the storage is very important, and there are much more options beyond batteries. With that, I'll end my presentation.